started. Let's open up our texts to lesson number 7, and or you can open up the slideshow for today. Okay, let me let our friends in. Good morning, everybody. Good morning. Please open up either your textbooks or the slideshow for today. Good morning, everybody. Please open up your slideshow for today and or the textbook to lesson number 7. Okay, Connor is here, Junior, John, and Kyle. So we're just waiting on Janessa, Cameron, Tyler, and Eva. Okay, I'm going to share my screen and we are going to get started. So here we go. Let me go like this. Give me a moment just to, Tyler is here. Good morning. Let me get the participants up and over here. Let me get the chat up and over here. Here we go. Okay. So we have our either textbooks or slides open to today, and let's get started.
I have a question.
Question, go ahead, Kyle.
Where should we open up our textbook?
To lesson number 7, 186. 186. If you're in your text, we're in 186. Here we go. Let me just turn my screen. Let me put my camera back on here just so you guys can sort of see me in all of this. And let's take a look at what we're doing for today. So our lesson for today, we're looking at and explaining steps for rewriting equations. So we're going to be doing just like we did yesterday, where we were looking Friday and Thursday, whereas we were looking at equations and we were saying what moves are going to take me from one to the other. We're going to be doing something very similar again today. So what I want you to do for the warm up for today is I want you to take.
Mr. Ellsworth, please call extension 3211.
I want you to take a minute and 30 right now to check, is 0 a solution for each of these equations? And then I want you to tell me why or why not. So what my suggestion is for the why or why not, you just put your what did you get for those final numbers, and are they equal to one another? Are they not equal to one another? Okay? So you're taking a minute and 30 right now to work on either slide number 2 or 186 in your text, the warm up for today. Here we go. Wonderful. My friends at home, once you start to get answers, let's number them 1, 2, 3, and 4. Give me some answers in the chat. Are they solutions? Yes. Is 0 a solution? Yes or no? Nice job, Gabe. Nice job, Abby. Thank you, guys. You're doing great. Nice job, Max. And my friends that are just giving me yeses and nos, that's fantastic. Be prepared. I might call on you to tell me why. Okay? Let me let Ava in. Oh, okay. Okay, bye. Here we go. Let's take a look at these guys here. Hey, Pate, do you mind sending Cam a message just to see if she's okay? She's just not in yet, so I'm just wondering if she's okay. Let's take a look at these guys for this one here. So I have some friends in the chat give me some answers. So if we look at one, Max said no, Abby also said no, Gabe also said no. Kyle, what were you thinking for number one? Do you agree with this idea of no?
Yes.
And why do you think that?
I got a bunch of stuff on this.
What do we think? So when we plug 0 in here, we got what is equal to what? Sort of Tanya up there.
1 minute.
Can you do, why don't you do 2 for me then, if you don't have it right now? What did we get here for this one? Thank you, Peyton. What did we get for this one, Junior? What is equal to what? Okay, so let me show you how this works. How do you test these guys? So you take the 0 and you plug it into the equation. You get 4 times 0 plus 2 is equal to 10, okay? That is equal to 4 times 2. So what is equal to what here? 8 is equal to 10. Is that true? No. So that is why this is not a solution, because 8 does not equal 10. Okay? This is what I'm looking for when I'm saying I need my answer, and then how, why, or why not. And that is what I'm looking for. It is equal to 10 or it's not equal to 10. Perfect. We substitute 0 in here. What are we going to get here? What did we think about this solution here? A couple people said yes for this one. What were you thinking, John?
Yes.
And why did you think that? 12 is equal to 12. Very good. Very good. Nice job. When you plug 0 in there, you get 12 is equal to 12. Very good. Now, when we look at our third one, we had some friends tell me yes in the chat here. Yes. Yes. What were you thinking, Connor?
The third one,
Yeah.
I thought yes.
And why did you think that?
Because if you put in 0 for x,
Mm-hmm.
you get 0 equals 0.
Very good. And 0 does equal 0. Very good there. Nice job. And then if we look at this last one, Gabe, can I have you unmute and can you tell me what you got for an answer for 4? What do we think, Gabe?
For 4, I got it wasn't a solution because when you input 0 for x, 6 divided by 0 plus 1 isn't equal to 8 because
Okay.
1 isn't equal to 8.
Good. So then it would be like 1 is equal to 8. But another real reason, the real reason behind this is yes, 1 does not equal 8. Another reason that you can say, and the more accurate mathematical reason would be because if you divide by 0, it's undefined, right? So an undefined plus 1 is still going to be undefined. So no, because it's undefined. Okay, I would add that in there because this is a very important idea to remember, that when you divide, 6 divided by 0 is undefined. So an undefined number plus 1 is still going to be undefined. So yes, if you're looking at it purely as like what plus what, it wouldn't be a solution, but it's really because when you divide anything by 0, you get an undefined value. Okay? Awesome, awesome, awesome. Let's take a look at the next piece of this here, our learning targets. We have 3 learning targets for today. Okay, learning targets are 1, I can explain why some algebraic moves create equivalent equations, but some do not. So, well, some do not. Better there. Meaning, what moves maintain equity, which moves do not maintain equity. Good. Next one. I know how equivalent equations are related to the steps of solving equations. Hi, this is Mr. Mann. Yep. Okay, that works. Wonderful. And then we'll figure it out moving back. Yeah. Awesome. Yeah. Okay. So I know how equivalent equations are related to the steps in solving equations. So when you're looking at steps, you're going to know they're equivalent if every single step that you take maintains equity on both sides. If you maintain equity, then they're going to be equivalent. Good. Now, last one is I know what it means for an equation to have no solutions and can recognize such an equation. This is a throwback to the last unit, right? We talked about no solutions. What did we say no solutions meant? If you're looking at an equation, what does no solutions mean? Friends can throw it in the chat if they would like. What does no solutions mean when you're looking at an equation? What's the same? What's different? Yes, Gabe. Yes, it would have no solutions. Good. But what else would we think, Junior? We have the same slope. Very good. So no solutions have the same slope or the same variable. What is different? Kyle? The constants, or if we're talking about like y equals mx plus b form, it would be that y-intercept. Good. And then I'm going to also put like in parentheses y-intercept. Okay? So we're going to be talking about no solutions, infinitely many, and like one solution. We're going to be focusing on no solutions today. We want to make sure that we remember what does it look like graphically if we're looking at a system. What does it look like? In an equation itself? Okay. Awesome, awesome, awesome. Very good, Max. Let's take a look at what we're doing for today. So the first activity for today, we're on slide number 3. If you're in your text, I think we're still on the same page. Yes, perfect. Okay, so it's been sort of broken up for you. So my suggestion is for this activity, you might want to do it on the slides just because if you're looking in your book, it doesn't really give you like separate room for these two pieces here. So what we're doing in this activity is it says, here are some pairs of equations. Choose a pair of equations from column A. Explain why if x is a number that makes a solution, the first equation true, then it's also going to make the second equation true. So why do these equations, what about them, what move can I do to the first one to get it so that it looks like the second one? So you're going to look at column A, and for each one, you're probably not going to get to all of them. We're going to decide what sort of move is going to maintain equity, what move happens from the first one to the second one to get that second one to be how it looks. Do you sort of get what I'm saying? So you're looking at them and you're trying to decide what move is going on here. Okay, I'm going to give you 5 working minutes right now to look only at column A. If you finish column A, I would love for you to move to the next slide, slide 5, to look at column B. Okay? Looking at column A, column B, talking about the moves that take column A, the first one in column A to the second one in column A. And then in B, it's going to be what moves don't maintain equity. So you're taking 5 minutes right now. If you have questions, throw them in the chat, okay? Awesome job, Peyton. Thank you for getting those answers in the chat for us. I love it. Awesome. You're taking 4 more working minutes to work on this guy here. These 5 sets of equations here, these 5 systems. If you finish early, ladies and gentlemen, you can move on to look at the ones on slide number 5 as well. Those ones are not maintaining equity, but you need to identify what move is not maintaining the equity there. I'm not saying you need to go quicker. You still have 1 minute and 30 seconds. Take your time with this. You're trying your best. How you doing, John? Awesome. Ooh, awesome job, Gabe. Looks like a good explanation there. Impressive, Gabe. And Peyton, she's doing fantastic. Nice one. Awesome job, ladies and gentlemen. You took 5 solid minutes. Let's take a look at and go through these now. And then if you didn't get all these copied down, that's okay. We're going to get them down now. So let me just sort of pull that up. Let me turn my screen again, and let's take a look at these guys together, okay? So if we're looking back at slide number 4, column A, if you're looking in your textbook, like I said, this one was a little bit easier to do in the slides because it gives us a little bit more room. So if we're looking at the first pair, so like 1A, what did we think was the move that took that first one to that first equation to that second equation? What move did we do there? Connor. So Connor said we distributed. Let me see what friends in the chat were saying. Good. Peyton said the same thing. She said multiply what's in the parentheses by 4, which is the same thing as saying distributing, distribute. Very good. Gabe said the same thing. Very good. We want to make sure that we give it that name, though, of distributing, right? We're distributing what's outside the parentheses into each of the pieces or the terms inside of the parentheses. Good. So we said that we distributed that and we could rewrite that. That first equation can be rewritten as 16 is equal to 36 minus 4x. I just got a plus on it. Minus, sorry guys. Minus 4x. Good. Does that move maintain equity? Yes, because we're doing the same thing from one side, or well, really we're not doing anything to the left side, but we're just doing something on that. We're simplifying on the right side. So that's maintaining equity because we're just sort of doing an operation that it tells us to do. It's sort of like when we combine like terms. Good. When we look at number 2, what do we say? What sort of move was taking 1 to 2? What did we do here? Junior.
Subtract 2x.
From where?
Both sides.
Very good. So you want to be really specific and you want to say we subtract 2x from both sides. What is the piece of that that tells you we're maintaining equity? If I'm looking at this description or this explanation here, what piece of it is telling me we're maintaining the equity? To both sides. Very good. Or when we're looking at those larger equations, we would say to each term. Very good. Nice job, Junior. This piece right here is telling us we're maintaining that equity. Very good. Now let's take a look at number 3. This one is a little bit trickier. What is the move that's going on number 3? There is one move that you can do, but what move would it actually take you from 1 to 2? John. Very good. We divide 3. We divide the negative 3 on both sides, or we can broaden it out. We could say to each term. Very good. Divide. Wait, let me write that again. Sorry. You said side. I also like the word term. By negative 3. Very good. We could have, one second, I'm going to check that chat. One second. We could have distributed, but I'm saying now, I want you to really look at it. What move takes us from there? We can, because all of these, because this is divisible by negative 3, the left side is divisible by negative 3, the right side is divisible by negative 3. You can simplify it that way. If you remember back, I said that sort of takes out a step and it gives you much smaller numbers than if you had distributed there. Good. Now let's take a look at number 4. What's going on number 4? Let's see. Abby just put this in the chat. Abby said they're the same equation, just in a different order. So the x will be the same. And then she said they distributed. Good. So we just are switching the order. Exactly. Very good. And that math term for that is the commutative property. So on the right side, we use the commutative property or we switch the order. We want to remember when we're switching the order of things, right? We need to remember that we need to maintain the signs. So in this case, this was a negative x. So you needed to, when you switch the order around, you needed to keep that negative with the x. You needed to keep the positive with the 3. So we want to make sure that as we're working, and if we're switching the order of things, we are maintaining the signs that stick with each term, each piece. Okay? Nice job there, Abby. Now, if we look at number 5, what's going on number 5 here? Kyle.
The x was added to the 3x. Can't remember the exact word.
Good. So he said the 3x and the the x came together, and the term for that is we are, what is that called, Junior?
Combining our like terms.
Exactly, we're combining like terms. And don't get tricked and say we're adding x to each side. Because we didn't add x to our left side. We're saying here that we are combining like terms. That means we're taking our x's and we're bringing them together. Usually we're adding them together to get, like, what do they come together to be? Good, nice jobs. Awesome job in that chat, guys. We're combining our like terms. Very good. Now, what I want you to do, I'm going to give you 3 working minutes right now to look at the next slide here. I'm going to keep this up for a moment, and I want to show you what you're doing on the next slide here, okay? So what are we doing on the next slide here? We're looking at column B now, and you're explaining what moves are going on from the first one to the second one, and you need to make sure that you're letting us know how it doesn't maintain equity. So because we're doing this, it doesn't maintain equity. I want you to take 3 working minutes right now to work on these 5 problems here. If you finished, I want you to stay here and just sort of take the rest of the time to think independently about these, okay? How are we not maintaining equity here? I'm going to erase this, guys. Nice job, Peyton and Abby, on that last one. I know I said it already, but I'm going to say it again. So on this one, we're talking about maybe what moves are we doing to the left side that we didn't do to the right side? What are the different moves that we're doing to each side? Make sure that you're really telling me how we're not maintaining equity. Awesome. We have about 2 more working minutes. We have another minute and 30 seconds for ourselves. What moves are not maintaining equity here? Nice job, Gabe. Nice job, Peyton. Both of those look great. Awesome job. Oh, 4. So 4 isn't going to maintain equity, Gabe. Just an FYI. So 4 is probably the most challenging one in this whole table. There's different things happening to both sides. Let's take a look. Nice job. Nice catch there, Gabe. Looks good, my friend. Let's take a look at this guy together. Okay? So, this first one, B1. What's going on in B1 here? What sort of moves are we seeing going on here? Kyle Kelly.
5x was added to the other side, but
Go ahead, keep going.
it was moving it to the other side, but instead of subtracting it, adding.
Oh, so we're adding 5x on the left, but we're subtracting 5x on the right, right? Awesome. So if we do different things to either side of our equation, our equal sign, what does that mean? What does that do? John, what happens when I add 5x to one side and subtract 5x from the other side? They don't equal the same thing anymore. They're not equivalent. It's not maintaining equity. So when you're doing different things to each side of the equation, that's not maintaining our equity. So I would say here, for our explanation, we add 5x to the left side, but subtract 5x from the right side. So we're not maintaining equity. Awesome. Okay, let's take a look at the second one here. Let's get someone at home to help me with the second one. It said 2. Only one part of the left side was multiplied. Good. So, Gabe said that when he was looking at this one here, he said only one part of the left side was multiplied by 2. So he multiplied, and what do we call a part? Think about that math vocab word. What do we use instead of part, only one part? What do we say? We say multiply by 2. We only multiplied this 1/2 x by 2, and then we multiplied our right side by 2 as well. So we only multiplied, what do we call that? Nice job, Ian. A term. We only multiplied one term. So this is where that idea of term really comes in, because you can't just say he multiplied the left by 2, he multiplied the right by 2. No, you need to multiply both terms or pieces on the left by 2, okay? So he didn't multiply each term by 2. Awesome job, Gabe. That was perfect. You need to multiply each part or term by 2, or whatever number you're multiplying by. So that's why this one did not maintain equity, because he multiplied the 1/2 x by 2, the 9 by 2, but he didn't multiply this -8 by 2. Does that make sense, John? Perfect. Awesome. Now, let's look at this third one. John, did you get this third one down? What did you think for this third one?
They only added 5 to one side.
They only added 5 to one side. Okay. So add 5 what?
They just added 5. They added 5 to the -6.
Oh, so he added 5. But then how did I go from the 5x to the 1x?
I didn't see that.
Okay. Good. I love it. Good attempt. We're talking about differences here. So you could add something, or you could multiply by something. So it's not going to be the add piece of it. How are we taking this whole left side and bringing it down to be the right side down there? What would we have to do? We're not going to subtract something, because you can't. So you would subtract 5x, but you can't subtract 5x from the 6 to get it down. So we're going to have to divide by something. What would we have to divide by to go from 6 all the way down to like a 1?
6.
Very good. So we divided the left by 6. Only, right? So we only divided, or I'm going to say only, divide the left by 6. We didn't do it. We didn't maintain equity and divide the right side by 6. Do we notice that? So our right side stayed the same and our left side got smaller. So if we wanted to have maintained equity, what would we have had to do here? We divided the left side by 6. We would have done what to the right side? Divide it by 6. Very good. So if we wanted to have maintained equity, we would have had to divide all of the terms or both sides by 6. Very good. So because we only did it to the left is the reason that it's not going to maintain the equity. Good. Now we're looking at 4. 4 is probably the trickiest here. We're going to take it side by side. Okay. So if I'm looking at this guy here, if I'm looking at the left side of the first equation, if I'm looking and comparing my left side on the first one to the left side on the second one, what's going on? What happened or what got rid of or what got added? If we're looking at only the left side here. Junior, what do you notice?
I distribute, and I made it, and like you would have had to add 11 to the left side,
Mm-hmm.
try to cancel it out, and then add 11 to 8. But instead of like doing it right there, he added 11 on the right side of the equation.
So we added 11 to the right side. Good. Awesome job, Junior. We added 11 to the right side. What did we do to the left side? Look at how the left side changes. It was negative 11, parentheses, x minus 2. And then it went to just an x minus 2. Let's see what people are saying here. So the left side, Gabe is saying the left side is divided by negative 8. Good. So we would divide left by negative 8 or 11. You said 11. I'm sorry, Gabe. I just was thinking 8. I don't know why. So we're doing 2 different things to the left and to the right. What are we doing to the left again? What did we do to the left? We divided by 11. And then what did we do to the right? Added 11. So if we want to maintain equity, we need to do the same thing. Go ahead, Kyle. So if we wanted to maintain equity, we'd have to choose one of those, right? We could either divide both sides by 11, or we could add 11 to each side. Would both of those moves separately would maintain equity. If you added 11 to both sides, it would maintain equity. If you divided both sides by 11, it would maintain equity. But because we're doing 2 different moves to either side, is where the unmaintaining of equity happens. Does that make sense? Do we see why? So you want to do the same thing to both sides to maintain that equity. Good. Now let's take a look at number 5. Number 5, we have these 2 guys here. What's going on here? This one's not too bad. Kyle.
They subtracted 4 off each side, and 5 somehow became positive.
Good. So we subtract 4 from both. Does that subtracting 4 from each side maintain equity?
Yes.
Good. So the first move maintained the equity, and then somehow we flipped our signs on that negative, on that 5, right? That negative 5. So what we did to flip that sign would be, we could say that like in math terms, we could say divide by negative 1, right? So we only divided by negative 1 on the right side. Only divide by negative 1 on the left side. Okay, so how we went from that negative 5 to that positive 5 is we divided by negative 1, okay? But we didn't divide the right side by the negative 1. So that's where the unmaintaining of equity comes into place, is because we didn't divide both sides by the negative 1. Do we see that? So that first move did maintain equity, The second move, though, was where we messed it up. Okay, so, oh my goodness, Mr. May just took a lot of time on that, but it's okay. Now, what we're gonna do, how we're closing off class for today. I'm giving you 6 minutes. I'm gonna give you 6 minutes. So I'm gonna give you another minute to write this down, and we're gonna look at slide number 6 sort of in the meantime, okay? So the next activity, if you're looking in your book, it's 7.3. It's called It Doesn't Work, okay? So Noah, he solved some equations on the next slide, okay? It's going to be your job to look at the steps that he took, and you need to decide where is his mistake and or where did he not maintain equity? What was right? Which moves were right? Which ones were wrong? You're going to look at 2 different equations that he ended up solving, and for each one, you're going to decide where those mistakes are. Let me show you what that looks like. If you're looking, I think for this one, you can do this one in your text. I think there's enough room there. Let's take a look at the layout on the slides, okay? So on slide number 7 is where the first one is. You're looking at his steps here. Remembering when it says apply the commutative property, that means changing the order of things, keeping the signs, okay? So you're saying which of these steps is right, which of these steps is wrong, and why? Hint, the first one, there might not be any actual steps within it that are wrong. It might be like something else that's wrong. Anyways, you're looking at this one, then you're looking at this one, where on slide number 8, number 2, where are his problems here? Where is he correct? Where is he incorrect? And or, go ahead, you're taking 6 minutes right now. Nice. Once you guys start to get answers for these, you can go like 1 would be this one. What did you think was correct? What did you think maybe was incorrect? Like I said, the mistake for the first one might be pretty far down. And there is a mistake in both of these. Nice job, guys. We have another solid 5 minutes of work time for ourselves. Wonderful. You guys are doing great. We have another minute and 5 seconds. 2 minutes and 45 seconds. Awesome. We're taking another minute 30. Let me know in the chat if you finished early. You can take a look at the questions on slide number, oh goodness, 9 that pertain to this problem. Okay, taking another 10 seconds. And there we go. So let's come back together. Let's take a look at these guys here. Okay. Did we think that there was a problem between steps 1 and steps 2? Nope. I think the commutative property works. So there's not a problem between 1 and 2. So I would say between 1 and 2 is good. Now, when I'm looking at 2 and 3, so step number 2, what did we think about that one? Did you do the right thing? Did he maintain equity? Well, what did he do? He combined like terms. Does combining like terms maintain equity? It does. Combining like terms does maintain equity if you do it correctly, right? So like if you have like a 2x and a 3x, you would combine them to be a 5. If you combine them to be a 1x, then you're not maintaining equity. But in this case, he did maintain equity because a 4x minus a 3x is in fact a 1x, right? And then this is where he starts to sort of go, I mean, it works. It could have worked. So he subtracted x from each side. And he's left with this solution of 6 is equal to 1. But if we look back at this step here, if we look back at step number 3, what do we know about the solution to this equation? Same, what, different, what? Looking at it, what do we notice here? Max, what did you notice? Max, unmute yourself. Let us know. What did you notice when you looked at this right here?
I noticed that he didn't keep like the variables. What he did is, oh wait, hold on, I'm on the wrong one. I noticed that between 2 and 3, what he did is he got rid of both of the variables when he was supposed to keep a variable on one of the sides.
Well, okay, so when we do that though, so he would be doing that. That was his sort of thing, was to get the x's over to the left. To do that, he would have to subtract an x, So then I would be left with 0x plus 6 is equal to 1, which can just be written as 6 is equal to 1. But if you look at this step right here, Connor, what do we notice? Looking at our left and our right side, what do you notice? Good job on that, Max. Same what? They have the same what? It has a 6 and it has a 1. Those are different constants. They both have constants, but the constants are different. The variables or our slopes are the same, right? Do we notice that? We have a single x on each side. So that means it's either going to have infinitely many solutions or no solutions. And then, so once you look at it and you determine you have the same variable on each side, then you need to look at your constants. What do we notice about those constants? They're different. So that means it's going to have no solutions. So when we get to, if you have an equation like this, right? I showed you earlier that you make a decision based off of this. If you decide to take it one step further and you're left with some number is equal to some number, different numbers, you can rewrite that as no solutions. Okay? So really he's missing a step here. He needed to take it one step further and say that when we have 6 is equal to 1, we write that as no solutions. Now let's take a look at the next one here. Number 8. Okay? Let's look at what he did here. All of his steps here, except for the last one, are acceptable. I'm going to erase that now. So all of them are good, except for the last one. Okay? Because applying the distributive property maintains equity, subtracting 10 from each side maintains equity, adding 1 to each side maintains equity. So now we go from here. We're dividing each side by x. We can't do that. You want to get your x's to one side. So what he really should have done here is he should have subtracted 2x from each side, then left with x is equal to what number? So this is like 2x plus 0, right? But we don't see it because it's not written there. It's implied. So it would be x is equal to, what's it going to be, Junior? It's going to be 0. So we're going to say x is equal to 0. That's a solution. We're not going to be able to say that no solutions is incorrect. Okay? If you were to look at this and you said this has no solution, that would be incorrect because dividing by x on each side does not maintain equity. You lose your variable that way. You don't want to do that. You want to combine your x's to one side and then say, if it so happens, 0 is equal to however many x. Does everyone see that? Good. Nice job. Fantastic. Thank you. Let's take a look at the last little bit of this. We have 2 minutes. I'm going to use those 2 minutes. Let's look at them. Okay? So we're not going to look at the questions on slide 9. We're going to slip and slide right down to slide number 10. So I think this is actually in your textbook. It's like in the lesson synthesis part of it. Okay? So if we look at A here, if we look at A, and we're looking at step 1 to step 2, equation 1, equation 2, what move is going on to go from 1 to 2? What am I doing to each piece of this? Each side of this. Nice job, Gabe. What do you think, Junior? Very good. We divide each side by 5. Does that maintain equity? Yes, it does. Very good. So will it have the same solution? If you maintain equity, if you say they are equivalent equations, it's going to have the same solution. Very good. Your homework for this evening, listen. Homework for this evening. There is an exit ticket on slide number 12. That is your homework for this evening. Tomorrow, I'm going to be giving you Alex time for homework as well. So just be aware. My friends that need to go to Spanish, please remember you have your exit ticket that is due for you today. That is due for today. If you can, so that means you can hop out and go to Spanish if you'd like. Connor can head down to Spanish if you would like. My friends that are at home, I need you to stay in if you are not a part of Spanish. And we are working on our Alex time for today. We are trying to get, oh gosh, we have like a district goal of like an hour every week. So this isn't going to be every week. We're not going to be doing Alex all day, every day. We're going to figure out a schedule and then we're going to sort of get into it. But for today, we're working on Alex time, your path. Okay. If you didn't finish the knowledge check, now is a good time to get that worked on as well. You're working on the knowledge check for Alex, or you are working on your path for Alex. Screen.